Okay, so in this video we're going to take a look at problems 9 and 10 on our sample final. So let's begin with problem number 9. It states, for which constant k is the following function q of x continuous for all x? Justify your answer. So we have q of x is equal to a piecewise function, x squared plus k if x is less than or equal to 0, and cosine of x if 0 is less than x. So to avoid confusion, I'm going to rewrite my second inequality as x is greater than 0. So now recall that a function f of x is said to be continuous at x equals a if we have the following checklists, right? The following three bullets. F of a must be defined, right? If you plug in some value of a into your function, it must be defined. The second thing is that the limit as x approaches a of f of x must exist. So equivalently, you can say that if the limit as x approaches a from the left, right, a minus means from the left, of f of x is equal to the limit as x approaches a from the right of f of x. Let's say if they're both equal and they're equal to L. Then you can conclude that the limit as x approaches a of f of x from either side is also going to equal to L. And now 3 is the most important part, is that the limit as x approaches a of f of x must be equal to f of a. In other words, 1 must be equal to 2. So if you want to begin solving this problem, or trying to figure out the value of k where the function is going to be continuous for all x, then we're going to need to compute left hand and right hand limits. So what we're going to do is the following. We're going to compute the limit as x approaches, well, in this case, a is going to be represented by 0. So we're going to look at the limit as x approaches 0 from the left of q of x, and it must be equal to the limit as x approaches 0 from the right of q of x. So remember, when x is approaching 0 from the left, note that the value of x are going to be less than 0, but it's going to get really, really close to 0. So for instance, you're looking at numbers like negative 1, negative 0.5, negative 0.1, and so forth. Now, if the limit as x approaches 0 from the right, then you know that these values of x are going to be greater than 0, but at the same time, it's going to get closer and closer to 0. So for instance, you can start off with 1, then 0.5, then 0.1, so forth. Okay. Now, we can go ahead and replace q of x with their corresponding piecewise. So we're going to have the following. We'll have the limit as x approaches 0 from the left of x squared plus k equals to the limit as x approaches 0 from the right of cosine of 0. Cosine of x, sorry. Now, because both sides, from the left and from the right, we're getting really, really close to 0, we can directly substitute 0. So what we're going to have is the following. We're going to have 0 squared plus k is going to equal to cosine of 0. Well, 0 squared plus k, that's just going to leave you with k. Cosine of 0 is going to be 1. So the value of k must be equal to 1. So when I plug in 1 for k for our function, then you should see that basically continuity is going to exist at x equals 0. So we'll have the following. We're going to have that q of x is now going to equal to x squared plus 1 if x is less than or equal to 0, and then we're going to have cosine of x for if 0 is less than x, or x is less than greater than 0. And that'll be it, right? If you wanted to, you could have went through the checklist, but I'm going to move on to the next problem. But again, you'll see that when k is equal to 1, the function is going to be continuous for all x. Alright, let's look at problem number 10 now. Problem number 10 states, show that the derivative of f of x equals 1 over x is the derivative of f prime of x, is equal to negative 1 over x squared by using your limit definition of the derivative. Well, our limit definition that we're going to use is that f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x divided by h. So if you don't use this limit definition, unfortunately you will not get any credit for this problem. So here goes. Oops, I hit the camera. We're going to have the following. We're going to have that the limit, we're going to have f prime of x is going to equal to the limit as h approaches 0. Now I have to figure out what will be my f of x plus h piece. Well, wherever I see an x, I'm going to replace it with x plus h. Well, since I have 1 over x, then that's going to give me 1 over x plus h minus the original function, 1 over x. So I use, so as I done in when we were doing this problem in class, I like to keep these two pieces, f of x plus h and f of x, separate. I like to use brackets to separate them. And you're now going to divide by your h. So what we need to do is combine our fractions in the numerator. And when we're going to combine our fractions in our numerator, what we'll need to do is determine the LCD. So if we determine the LCD between x plus h and x, right, the LCD of x and x plus h is their product. It's going to be x times x plus h. So for the fraction 1 over x plus h, I'm going to multiply it by x, and for the fraction of 1 over x, I'm going to multiply it by x plus h, top and bottom. Now why do I need to find the LCD? Is because I want to combine my two fractions into a single fraction, and if you notice, the denominators are not the same. So we'll have the following. We're going to have the limit as h approaches 0 of 1 over x plus h times x over x minus 1 over x times x plus h, top and bottom. Now don't forget that we have to divide by an h. Yeah, just don't forget about the division of h. Okay, so let's simplify this as much as we can. 1 over x plus h, when you multiply it by x over x, you're going to get 1 times x in the numerator. In the denominator, you're going to get the product of x times x plus h. You don't have to multiply that or distribute the x into your parentheses. That's okay. Minus, here you're going to have 1 times x plus h. So you'll have x plus h in the top. And again, in your denominator, you're going to have the product of x times x plus h, all divided by an h. So now that my denominators are x times x plus h, I can combine my numerator. So I can create a single fraction. Let's see if I can just do it within this page. So what we're going to have is x minus x minus h in the numerator divided by x times x plus h, all divided by an h. So it's the limit as h approaches 0. Again, in your numerator, it's going to be x minus x minus h. Why? I have to distribute the negative inside in my brackets. So it's negative x, negative h, divided by, now, since my denominators are the same, I could just rewrite my denominator as x times x plus h, all divided by an h. So what we can do now is simplify the numerator. You're going to have the limit as h approaches 0. X minus x cancels each other out, right? That's going to be 0. So you're left with negative h over x times x plus h. Now since I have this division of h, rather than dividing by an h, if I were to write that as h over 1, I can multiply by the reciprocal, 1 over h. So h over 1, again, I'm just applying this keep, change, flip, keep the simplified form, which was negative h over x times x plus h, change division to multiplication, and now flip h over 1 as 1 over h. So if you notice now, you're going to have an h in the numerator and an h in the denominator. So your h's will be canceled out. As long as h is not equal to 0, they're definitely going to cancel out, and what you're going to be left with is the following. Well, in the numerator, you're going to be left with negative 1, so it's the limit as h approaches 0 of negative 1 over x times x plus h. And now what you can do is directly substitute 0 for your h. So we can compute this limit. Well, you're going to get the following. It's going to be negative 1 over x times x plus 0. Well, now, if you were to distribute that x that's on the outside of your parentheses, you're going to get x squared plus 0 times x, which is 0. So your final answer here is that you're going to see that f prime of x, your derivative now, is going to be negative 1 on the top over, well, if you distribute your x, you're going to get x squared plus 0, which is just x squared. And that is exactly what we wanted. We wanted to get that the derivative of the original function, 1 over x, is negative 1 over x squared. So that's our final answer. Now again, it's just important to note that you have to use the limit definition of the derivative. If you don't, you're not going to get any credit for this problem.